use this device, which is just a box. It's periodic boundary conditions. So what goes in on one wall comes in through the other. And it contains a fluid of constant density rho and fixed viscosity. And the viscosity is small. It's only to make the Reynolds number very high. And it has a size L, let us say. Now, somehow you shake the box. You shake the box at a velocity which is of order u. And then you combine these three things, velocity, length scale, and viscosity, to give you the Reynolds number. And I said viscosity is small. Somehow that is to say that the Reynolds number is very high. So that's where we want to go. And as soon as you do that, nonlinearity somehow spreads energy into all length scales which are smaller than L at which you start. So nominally, the smallest scale reached is eta, as I have shown, and it is proportional to Reynolds number to the power minus 3/4 in relation to L. And if the Reynolds number is very large, eta and L are very far apart, so you have a thing called the inertial range in between, which is supposed to be universal and whose properties we will explore. For exploring these various things, we created three-dimensional boxes like this, which had, in the smallest case, 256 grid points along here, similarly elsewhere, so it's 256 to the power 3, and then going all the way up to 16,384. That gives you a certain Reynolds number, which is really like the square root of the Reynolds number in which we are often interested. But the important thing is the ratio between the large scale and the small scale increases like this at the highest Reynolds number of the order of a couple of thousand. And in these cases, we had enough statistics. Okay, I already said that. So we average over many realizations, so excellent statistical convergence, which you should not worry about. But we also have more recently a much bigger box, 32768 cube, which is 35 trillion grid points now, using the biggest computer there is. And in that et al. Somewhere, P.K. Young et al., you will also find my name somewhere there. So this we have not really explored yet, but this is something to do when we have more time. Now, by the way, whether you do the circulation by the line integral or using the Stokes theorem by the vorticity flux, it's the same answer as you should get. Now, let's do this one thing. For simplicity, let's take and one which is, this is a square and this is a rectangle with differences between L1 and L2. The question we will ask is, if they're both of the same area, what happens to the circulation? You might have some guesses on this. Will it be different or will it be the same? Now, as long as L1 and L2 are both in the inertial range, we will explore what the properties are. You may be surprised that, in fact, you take rectangles, aspect ratio 1 is a square, which is the red here, and then a rectangle with aspect ratio 2 there, and then a 4, which is a flat one like that. And what is plotted here is the probability density of the circulation as I go around in the box. So I put a box of a certain size here, calculate the circulation around it, move the box elsewhere, I get another value like that, and it will be a random variable technically, and then you will get a distribution, which is what it is. You can see that for all three boxes, you are getting the same distribution. And also notice on the vertical axis is the probability density function, which goes by about, let's say, 8 to 10 orders of magnitude, circulation being here. So it looks like it doesn't matter whether it's a slab like this or a square, as long as both lengths are within the inertial range, the probability density of circulation is the same. So basically, I say the circulation statistics are sensibly independent of the aspect ratio of the loop. Sensibly because there are maybe some small differences here, but then there are such low probability events. Even though we had a lot of data, it is possible that you could have some differences. And this area rule, which is what we call it, the independence of the properties on the aspect ratio, is originally due to Migdal in 1994. And Migdal was talking about loop gravity things. And what it was trying to solve the Einstein's relativity equations. Now, instead of thinking of space as a continuous thing, you think of it as made up of lots of little loops until you get a smaller scale at which you cannot really think of it like a fabric. But he was thinking about that, and somehow this is how we adopted it in 1995 to turbulence to study what the properties might be. The area rule was therefore one of the important things we found, but let's do a little bit more testing of this area rule. And what is the next test? So suppose instead of looking at the probability, you look at the variance of the probability density on this axis and the area of the loop on this axis. As you see, the area varies by quite a lot, and the variance also varies quite a lot. And for each of these two sets of data, there are two symbols here, one circle and one square. And one of them is for aspect ratio 1, the other is aspect ratio 4. And these two curves are for two different Reynolds numbers, small and medium. Now what you see is that, in fact, the numbers are essentially independent of the aspect ratio. 1 and 4 give you the same thing. And of course, it changes a little bit with the actual magnitude changes, but the scaling is also the same. You see, these are the two objects around which circulation is computed. And because of this independence of the aspect ratio, you can only consider squares henceforth. We have established that quite nicely, and therefore it makes your life a little bit simpler. Otherwise, you will have to do it for different aspect ratios, etc. And also, another thing is that in the classical Kolmogorov scaling, which is I call K41, which is 1941, so many years ago, velocity is scaled like the size, linear size to the power 1/3 in turbulence. And therefore, circulation, which is velocity times the length, will have to go like 4/3 power the linear size. And if you take the square root of it, of course, you will have the 2/3 power, which is what the dashed lines indicate. So that, I think, is already telling you that the Kolmogorov scaling is more or less correct. Now, let's do a little bit more complicated thing, which is this loop. Now, what you do is, let's say you start somewhere here. You go around the loop like this, and the area, the loop itself is to your right as you traverse this. But you get to the top loop, the area is to your left. So now you are in a bit of a quandary. If you think of the area now, the sign on the area is depending on whether it is to your right or to your left. Should you add up the two areas when you calculate the circulation around the area and attribute it to the area? Or should I just take the arithmetic combination of the two? It's not so easy to settle, but luckily you can make a small theory. If the scalar area matters, that is to say, you just add up the two areas, then I can easily show, K41 holds as it does, that the variance should go like area to the power 2/3. That's very simple calculation. But if I have to add the various areas as vectors, then skipping one or two lines here, the variance of the circulation will go like 1/3 over the area. Of course, 1/3 and 2/3 are sufficiently far apart. There can't be any ambiguity when you make measurements. And indeed, what you see is 2/3. It's nothing to do with 1/3. So what it says, this is for L1 minus L2 is eta, 16 eta, like that. Again, area here and the standard deviation there. And you can see that, in fact, it is 2/3 and not 1/3. So we have already made significant progress on this, which is that the scalar area rule holds. So one may consider only simple squares. It doesn't really matter how you do it. Now, when you take a square of area A, I can take the square root of A and call it R, which is the length scale for the problem under consideration. Okay. Now, what if you have non-planar loops, like the soccer gate or football gate, as you might call it? So what I'm going to do is I will go along here, go up like that, and like that, and like that, and come back here. Now, each side is square root 2R. Now, is that the right area for me to consider? Or that area is 4R squared? Or should I consider that as the area, projected area, for instance, of this soccer gate, which is now in more than one dimension? Actually, so that's the area of the red dashed line, 2 square root 2R squared. Which locally the curvature is 0 everywhere. So if you have curvature in one direction to be something, the curvature in the other direction is just the opposite, so the sum of the two is 0. So I have, let us say, two little loops, and now there is a surface tension will make a soap bubble, for instance, of a certain shape between the two of them, and that is the minimal area. It just happens to be like that. And this is minimal areas of great interest in not only fluid dynamics, it is related to surface tension and things like that, but it is also related of great interest in mathematics. If you look at modern subjects in mathematics, a minimal area comes in at many places. So now how do I know minimal area is the right one? So we computed the minimal area for this configuration. So it has to be done not so trivially. There is a MATLAB program you can write, and that's what gives you that. So it doesn't look all that great, but the picture. But you can compute the area, minimal area, to be 3.24 R squared, which is neither this nor that. And it turns out that is the right area to use for the circulation in order for it to follow what you see in planar things. So that is something to say. Area rule works for the minimal area. To summarize, area rule works as long as you use the minimal area. For, of course, on planar things, the circle you draw on a plane is a minimal area after all. Stokes' theorem doesn't necessarily say that the area has to be in plane. It could be anything that circumscribes this area, but the minimal area is the one on a flat surface for that. But for other things like the three-dimensional contours that I showed you, it could be different. Now you can ask, is it exact, or is it really a good working approximation? Will it get better with increasing Reynolds number? This will take us a little far, so I will not explain any of this, but let's pretend that this is a good rule for us, and now explore what it tells us about turbulence. So what I have plotted here is the cube of the circulation around a contour whose length scale is R, divided by R to the power 4, and its probability density. Now you must ask, why the heck am I plotting this particular quantity? It has to do with the tradition in turbulence. And by the way, there are many symbols there, 5 symbols, and 80, etc. to 300 and scale. And the tradition in turbulence has been that you would measure a point properties like here and here, 2 points, and usually you would consider the difference in velocity between those 2 points, and that's delta UR. And it is the universality of this delta UR that people have been engrossed with for the last 80 or 85 years, something like that. And I have myself spent a considerable part of my life on just that. Now what's happened is the focus of attention, instead of being point quantities, has now moved to circulation, which is an average kind of thing. And therefore, you might expect certain simplicity to arrive. And in fact, that is part of what we will describe now. And you don't have to follow this. Basically, it says why this third power is an important thing for us to consider, divided by r to the power 4. But if you're not particularly interested in the logic, you don't have to worry. But if you are, that's the answer to it. So it says that is in fact it's pretty well plotting on each other for these different sizes. In fact, if you go, let's say here, very tail end, in fact, go even further, up to probability density like 10 power minus 10, or here also about the same, the tails begin to show a little difference, but that is such small probability that you wonder whether, in fact, if you had more data, it would collapse or not. But okay, never mind, we take for what it is, but that is, for a big majority of the probability density, it is universal on this plot. Probably there are some differences for higher extreme tails, but I don't know the answer with great certainty. Now you looked at the third moment. What I will do is look at all other moments. Essentially, it's all contained in the probability density, but it is conventional and very informative to consider moments of order 2, 4, 6, and 8, as I have said, against R, which is the linear size of the loop that I am considering. And what is plotted here is the second moment, which is that, and the fourth moment, which is this, sixth moment, which is this, eighth moment, which is this, like that. So if you have similarity in the problem, or universality to it, so to speak, now there is a certain range here, range of scales, mid-range, over which these data have to plot on straight lines. In fact, I have done a little bit better in this inset, which is to take local slopes between 2 points next to each other, and plotted this for 2, 4, 6, and 8. And also I have plotted with these lines the Kolmogorov value, and this is 1941 thing. So for second order, it is, first of all, I want to show that in between these two, it's almost flat. And the line here is Kolmogorov, as I said, and the value is Kolmogorov as well. You go to fourth order, however, there's a little departure, but still it is plotting horizontally here. And you go to sixth, it's departing from Kolmogorov a little bit more, and for eighth, even more. So that's the behavior. And I'm going to plot this, summarize all this in the next plot. Okay, exponents fall below Kolmogorov 41, but not by much, as I said. I summarize all this in the following picture. And this is the order of the moment on this axis. And here are those exponents, that is the slope of those lines. And I plot them for each order p, and this is how it comes out. If Kolmogorov were the right thing, it would plot on this line continually forever, and its slope is 4/3. But what really happens is that it plots on this line up to there, and thereafter it departs and it goes on another straight line. So I have two straight lines now. Instead of a curve, which is a complicated curve for the velocity increments, this delta UR, instead this seems to be much simpler. And so I wrote here, the low moments reside on the space-filling set of dimension 3. The Kolmogorov thing is space-filling, and it has dimension 3. Whereas the high moments reside on another fractal set, because it's also a straight line, and it turns out it's a dimension of 2.2. So turbulence now has, if you're interested in low moments, you don't need to worry about all the intermittency and all this stuff. But you want to consider high moments, it is this, and it is much simpler than anything that velocity differences actually possess. So the conclusion so far is that circulation in wall-free turbulence has simpler properties than velocity increments. Are there other instances of bifractal behavior? This is all from our data, so you want to know if anybody else has done similar things. It turns out that this quasi-2D homogeneous and isotropic turbulence, a paper that appeared in PRL in 2023, that too has similar behavior. And similarly, in quantum HIT, you have two papers, one in Nature Communication and other in PRX, also similar behavior. There's also another one which was flow through a contraction that also has a similar behavior. So the answer is that I have a bifractal behavior instead of a multifractal behavior, which Professor Bala talked about earlier in the other room. So the intermittency of circulation is much simpler than this multifractal behavior, and all I need to know is this bifractality. Okay, now what is the nature of scaling of circulation in wall turbulence? I've told you so far about what happens if you're away from the walls everywhere, and you get to the wall and you find out what it is, and I want to take some time to interpret the results. This will conclude my talk. So now to do that, you do again numerical simulations of a channel flow, which is two parallel plates through which the flow grows under some pressure gradient. And it's solving Navier-Stokes, periodic boundary conditions in two directions, that is horizontal and span-wise, but no slip conditions on the top and bottom. And these are all the data which you don't have to worry about. The only thing that is of importance is the so-called friction Reynolds number, which is here. And roughly speaking, the Reynolds number of the flow would be 20, 25 times larger. So that's what you have to consider. So that's sufficiently high. So what I would also do in these two plots is that I take a cut parallel to the wall, and this is on the center line of the channel, and this is very near the wall. Now I draw a contour here and go through circulation again, and circulation here, and I'm going to find out what the differences are between the two and everything in between. So now I measure again the probability density of circulation against circulation here. And what we find is that these are all different different lengths for the rectangle. I want to first find out whether area rule works here also. So this is 43.7 by 43.7. In some units is just a square. And if you go here, it is now a rectangle which is about 10 times in one direction compared to 1 in the other direction. Except for this, which is now already a very long, elongated thing, you can see that everything else collapses on each other. So this simply says that one of these scales lies outside the inertial range, and therefore you cannot consider that. So basically, it says that I will ignore that for now because I've already gone through this in the wall-free case, but it confirms again whatever we saw in the wall-free case. So if you measure the center plane, this is what this is all about. It confirms that the area rule of circulation is true in the inertial range. Circulation properties depend essentially on the area of the loop, not its shape. Of course, we are generalizing a little bit here because I only consider rectangles. I could have considered stars and hexagons and all that, which I have not done, I must tell you. So what is the thing? As for homogeneous isotropic turbulence in a box that I described before, only square loops need to be considered further, which is what I will do. Okay, we got this far. Now let us see what you find for other moments. I looked at the probability density, but I want to look at the moments in particular. So these are all moments of order p, where p varies from one curve to another, and it increases. You go down like this from p equals 1 to 10. Okay, so that's what you find. So the slopes of these lines are the exponents in which we are interested in, and they are plotted here. The slopes here as a function of the order here. Again, you see that up to a certain order, maybe 3 in this case, it may lie on this red line, which is the Kolmogorov one, and then again it is lying on another straight line, just the same way as it did for homogeneous isotropic turbulence. So basically it says that if you're in the center plane, you should expect more or less things to be isotropic and homogeneous, which is what this is confirming for you in some detail. So the outer part of the channel flow has the same circulation characteristics as homogeneous and isotropic turbulence. This simplifies things enormously. Now we want to approach the wall. So I approach the wall, and the distance from the wall is measured in terms of the so-called y plus, and y plus of 5 is very close to the wall, and I can increase it, go more and more until I hit the channel center line, which I already know what it's about. So this one, I repeat the same thing. These are the moments of order p. P equals 1 to 10, I believe. And then here is the area, and I want to look for straight lines in this thing. And I am plotting the slopes as a function of p. Now this is at the center line, which I already described. One straight line, which is Kolmogorov, another which is non-Kolmogorov, but a straight line nonetheless. Now what you find is, as you get closer to the wall, it stops being on the Kolmogorov line altogether, and it becomes just one single straight line. So instead of the bifractality that you saw in homogeneous isotropic case, you now have monofractality, let's say. And the dimension of this monofractality is 3, because all straight lines have dimension 3, which is that they're all space filling. But this thing here, the slope changes, and we will ask, what does it really mean, and what are the big implications that it might have for our understanding of turbulence. The scaling structure is a monofractal throughout the inner region, space filling nonetheless. This is the paper in which it appeared. So let me summarize this so we can have a common basis on which to discuss it a little bit. And the summary is that for 80 plus years, universality has been sought in terms of velocity increments motivated by Kolmogorov, for which the picture is known to be quite complex. In fact, I am one of the very small number of people who have looked at it in great detail. It's not only a multifractal behavior. The multifractality depends on which component you're looking at, and therefore you need to have so-called joint multifractals. It all just gets more and more messy and more technical. Now, the second point is that the circulation statistics seem to be more amenable for the study of universality. In particular, the area rule makes it very nice. So here is the area rule with the minimal area, true away from the wall and so close to it as well, so essentially everywhere. And the low moments seem to be closely but not exactly K41, but high moments reside on another fractal set. Now, when I say it's not exactly so, I am going to maybe take you through this a little bit more. When I say it lies on the Kolmogorov line for low moments, if you look at it in greater detail, it's not exactly there, but it's slightly different. But I will explore the meaning of that in a little while. Bifractal behavior is common to other forms of turbulence as well, and it simplifies to monofractal behavior near the wall. And this changes with distance from the wall in the inner region. But below about y plus of 5, nothing really changes, so it sort of asymptotes to some constant. Now, what do these results mean? So that's the main question we should ask. So let me give you some definitions and background first. Delta UR there, the first bullet, is the velocity increment between 2 points which are sitting next to each other, R being the separation distance between them. And this is what I said Kolmogorov started with. Now it's conventional to write this as R to the power h of x. And this h of x is the so-called Holder exponent that is characteristic of the property of velocity difference locally. Now, if the velocity were a continuous function, this delta UR will have to go like R to the power 1, right? I mean, this is continuity from one position to another. But if you're in the inertial range, the point is that h is not unity. H is a fraction. And the value of this exponent tells you the singularity strength. That is, when you shrink it to 0, the velocity difference doesn't go to 0, but it actually blows up. This is the sense of singularity. And the smaller the h, it's very easy for you to figure out yourself that it's more singular and therefore more intermittent. Now, d of h fractal dimension of this singularity strength, h. So in other words, if in the whole flow, there are different places where you have different h's, you collect all those places where h is some common number and calculate the dimension of it, that is basically the volume of space it occupies, then the d of h corresponds to the fractal set, but basically just the volume that it occupies corresponds to given value of h. It tells how many points possess that local scaling of h. Now, it's very difficult to measure this because locally you have to plot delta UR and fit it by power loss and things like that. But instead, what one does is take the peak moment of delta UR, the angular brackets is the average, and you write it as R to the power zeta p. These are the exponents that we all have been talking about. I measured different order moments and calculated the slopes, and those are what is giving me this zeta p's. Now, the thing is, there is a Legendre transform relation, which you would know from thermodynamics and such things, that you can connect h and dh to p and zeta p. Now, this is a very simple relation. Now, the crux of the thing is that Onsager's theorem says that weak solutions of incompressible Euler equations can dissipate energy without viscosity, provided h is less than or equal to 1/3. So let's see what this means. What this means is that we have always been taught in school, I mean in college, in fluid dynamics, let's say turbulence course, that as the viscosity goes to 0, the energy dissipation remains constant, independent of viscosity, as long as the viscosity is small. Somehow, the thing goes, this is how Professor Narasimha taught me and how I used to teach also. That is, somehow the presence of viscosity is important for dissipation, but its value is not important. Now, this is always a mystery. How does this happen? You might say, well, the boundary layers that get thinner and thinner, and you have large velocity gradients as the viscosity goes down, and so everything is good. But why should it go in that fashion, right? It's not very obvious at all. But this is so a kind of mystery. I called it the zeroth law, by the way. But it's also known by the name anomalous dissipation. But Onsager said this: look, in turbulence, dissipation does not have to happen by viscosity. It could happen because you have singularities, like the ones I have shown here. If you have singularities, all bets are off. You will have dissipation. There's no mystery to it at all. And so he actually had a conjecture that says weak solutions of incompressible Euler equations, that is no viscosity whatever, can dissipate energy without viscosity, obviously, because it's Euler, provided h is less than or equal to 1/3. That's the theory, that's the conjecture of Onsager. But now it is a theorem of Onsager because it's been proved. It took many, many years. He conjectured it in 1948 or something like that. But it's now a little small industry grew around it, and they use a thing called convex integration, which I don't understand. But they have now this theorem. So what it means is that if you measure h, and you find that to be less than or equal to 1/3, then you have anomalous dissipation. This also has an important implication for Kelvin's theorem. Kelvin's theorem says that if you have no viscosity, the circulation on a Lagrangian loop remains the same. But if you have singularity somewhere, that can't be true, and you will have some leakage of circulation. So that's the important part of this whole business. And what have we found? We have found that lambda p is 4/3 times p, as I said, HAT. The Legendre transform says that this h delta u, which is what I called h earlier, is just 1/3. Classical Kolmogorov says that in the Onsager picture, delta u are always going like h to the power 1/3, one number everywhere in the flow. And the theorem says whether it is less than or equal to 1/3, then it's singularities. But if it is just equal to 1/3, this is the borderline case. And this is the classical 41. In fact, it says that if the exponent is not 4/3, but slightly larger than 4/3, then Onsager singularities do not exist, and dissipative anomaly, or this dissipation going to finite value as viscosity goes to 0, does not hold. And in fact, I could convince you by looking at the data that it is slightly larger than 4/3 when I said it is actually on 4/3. But I will stretch your goodwill to some degree, so I will just not worry about that. Next thing. Second fractal set is lower dimension, higher h, and therefore it represents higher Onsager singularities. They're irrelevant for anomalous dissipation because anomalous dissipation is the first order quantity, like the mean value. But nevertheless, I made that remark, and I'm happy to go back to it later on. Now for near wall. Near wall, we have monofractal sets, all of which are space filling, that is dimension 3. But the velocity increments are becoming progressively stronger as one approaches the wall, because the straight lines are becoming less and less straight as you approach the wall. And there it reaches some asymptotic state somewhere for y plus of phi. Now that has some important implications. That is, for y plus of phi, you can actually, from the experimental data, get this h, and you can calculate this, and it actually is very small. In fact, it goes negative, which implies extremely strong Onsager singularities. Now, let's speculate a little bit on what all of this means. All of this means is that in Onsager, with respect to Onsager theorem, probably in the bulk of the flow, that is, flow without walls, for instance, or very far away from the walls, so the walls don't have any influence, you may have dissipative anomaly. just on the border. In fact, if the exponents are slightly different from 4/3, it is not there. I mean, it looks very close to being anomalous. That is to say, you plot the dissipation with decreasing viscosity, it comes down and it remains flat. Instead of remaining flat, it may just slowly ever, it might, when we reach some building nearby, it may just go to 0. That is, in the highest possible Reynolds number you can conceive of, one of the basic relations of turbulence about this finiteness of dissipation as the viscosity go to 0 may not actually work. Okay, let's leave that for now. And then let's talk about Kelvin's theorem. And as I said already, if you encounter circulation, if you encounter singularities, circulation need not remain the constant. So d gamma or dt, big D, both denominator and numerator, everybody knows it should be 0 according to Kelvin, but this says it doesn't have to be. It doesn't have to be like that at all. And the Joukowsky theorem actually is interesting, how you can say that the circulation around the airfoil, of course, could be true, but all this nonsense about how does it actually happen? What I was taught was there was this so-called starting vortex, and the starting vortex takes certain opposite circulation to the circulation around this loop like that, and the sum of them remains always 0, which is what it was to start with. And who is to say this works when the starting vortex is, let's say, not in Chennai, but Sri Lanka somewhere? You see? I mean, I could never convince myself that that was true, but actually this gives some idea that it need not be true at all. So, okay, that's my pitch for you about the value of studying circulation instead of local quantities like velocity. You should expect some simplicity because circulation is an integral quantity, and therefore it is you should expect some simplicities. But the thing is, circulation is not an unknown quantity to us all. We know about circulation a fair bit in the context in which I brought up. And so it looks like we can make some progress in all these scaling problems this way. And with that remark, I thank you for your attention. This was the view from my window at one time. Now that I'm not an administrator anymore, I don't have that office with the same window. It's now pretty routine view. So thank you very much. So if you have questions, I can answer, but you don't have to ask me any questions. Yeah. Yeah. These are all numerical so far, but we have in the old PRL that I showed in the first transparency, we had made measurements, and they were lower Reynolds numbers, and PIV and all was needed, and the resolution was not very good. So we actually had some results which are very similar, but not as convincing as I think these are. These are all DNS, yeah.
Srini, yeah. I have a here.
Ah, okay. I saw another hand somewhere, but yeah.
You showed that circulation is bifractal or even monofractal.
Yeah.
Now, the velocity difference could be somehow connected to circulation also.
Yeah.
So could one back out the more complex fractal from the simpler fractal?
This I don't know the answer to, which one should be able to. So what is circulation? You sort of, in a square box, it will be velocity difference times this, velocity difference times that, added twice. That's what it is. So in principle, it's just can be backed out. But what it has, however, it has longitudinal in one case and also transverse in another. So it is mixing up longitudinal transverse in a certain way. And one of the difficulties with velocity differences is that the longitudinal scaling and transverse scaling are very different. And the transverse ones exponents saturate like this, while the longitudinal will keep going up. And so far, nobody has a theory for both of them together, except that my former postdoc has now a giant multifractal and things. So it just makes it very complicated. But one should, in principle, be able to back out. But because it is complicated by the transverse and longitudinal behaving differently, in principle, it's possible. In practice, it's very hard. Yeah. Rama?
So near the wall, everything is organized into streets.
Yes?
So is that the reason that you get a monofractal?
I think so, yeah.
Okay.
Yeah. Yeah.
And is it isotropic, like this way and this way?
Yes?
Wow.
So why does, why does looking at circulation make it as simpler as it does?
Yeah.
As you described?
I already partially answered it. Instead of focusing on local quantities like velocities, you're now doing an integral quantity, and also it has a relation to vorticity. And maybe it is the vorticity that really has some universal properties, not, let us say, potential flow also taken together. So these are all speculations for now, but that may be the reason.
So it's sort of a related question to that. So, so the fact that you have this monofractal nature far from the, far from the wall, can you write some effective, let's say, fluctuating hydrodynamic equation and then extract these for circulation?
This is very possible, and my former colleague Migdal, whom I cited already, has in fact been trying to do that. Now, Migdal was a professor in Princeton for many years, and at one time he was also an inventor, so he had a certain invention. He thought he could make money out of it, and took leave of absence from Princeton and went off to Wall Street. After 2 years, Princeton gave him an ultimatum: you either come back or you go off. He went off. He wanted to make money. So after we wrote this paper, he came to my office and said, I'm going to come back to physics full-time now. And he has come back to physics full-time, giving up all his money and working on problems related to that. If nothing else has happened, bringing him back to physics is one of the contributions of the work that I've described.
So I just have one quick follow-up.
Yeah.
So in critical phenomena, you have the partition function, whatever, is with some important quantity, right? But for this, the fact that you see this monofractal nature, does it also imply there is some underlying, I don't know, distribution which is preserved somehow coming from circulation? Or?
I think Rama pointed it out to it. But this is a speculation, but a very plausible speculation. Yeah.
Hello, yeah. So actually I wanted to ask that the third moment has an exact relation, which is proportional to R, delta V cube. So I was asking if the moment, is a particular moment of omega gamma cube, does it have an exact relation? Like Kalman.
I only heard part of the question about the third moment. Could you repeat your question?
So I'm saying for an isotropic homogeneous turbulence,
yes,
delta V cube goes exactly like R.
Yeah.
So is there an exact relation for gamma cube?
Yeah. So we know the exact relation for velocity differences, but we do not have an equivalent for the circulation. There is no theorem that tells you the third moment should in fact behave in a certain way. So that part of the thing remains to be done.
Okay, just one more question. So because you're saying that it averages out the delta V's over the box, I was just wondering whether the scaling holds when you go for higher moments.
Yeah, that's what I showed. For higher moments, you will have one straight line up to some moment and then another straight line up to another moment. That's beyond a certain moment. Presumably, it goes all the way. I have actually a little bit more to speculate, and that is you have two lines meeting at this point. Now, what happens if I increase the Reynolds number? My experience is that point moves more and more on the original straight line. That is to say, it remains approximately Kolmogorov for higher and higher moments, presumably for infinite order moments, which you can only speculate about. They all fall probably on the Kolmogorov line, in which case life becomes a lot simpler. But this is total speculation, and I could not make it, except that I know you're all very friendly.
So just last question. So you said delta U going like r to the power 1/3.
Yeah.
So the exponents, it could be slightly above 1/3.
Yes?
So I thought from most numerical results, we do see that it's above 1/3, right? Delta V to the power 1.
It is above 1/3 is what I think.
Yeah.
Slightly above
Slightly
1/3.
above. So you're saying that in that sense, anomalous dissipation decays in the large Reynolds number limit. I was wondering if you could tell how would it decay? Is it like a logarithmic?
Yeah, I can tell you how it should behave. What it should be is, if it is perfectly anomalous dissipation, then as you plot viscosity, let's say Reynolds number, which is 1 over viscosity on this axis, and the dissipation on this axis. Initially, when the viscosity is small, it will vary with viscosity, and it goes down, and then it remains perfectly flat. Now, the first evidence that was shown on that was my paper, 1984. But then, recently, I've been working at it for a very long time now. This was from experiments. But from simulations, I found that it was going down slightly, even beyond a certain Reynolds number. Whether it would have continued like that or not, I don't know, because I only have finite data. Now, so this is very interesting. If it is true, what it means is that without the walls, without real experiment walls, like periodic box, it will continue to go down and down and down, eventually to reach zero. That means homogeneous isotropic turbulence without the walls does not have singularities. Is this true or not? I don't know, but I'm just telling you what I can speculate. Now, if you want singularities in turbulence, which is one of the properties of turbulence, then you need a wall. It doesn't matter whether you have flat wall or whether you have bars across which the flow takes place. But wall somewhere is essential. So this reminds me of a statement that Hiroshi Sato once made to me. And he was saying, this was the time of chaos, when people were asking whether intrinsic instability, chaos gives you disorder, or whether it is just a noise which is getting amplified. And he said, this debate is not very meaningful. I think the right answer to this is, God gave us turbulence once, and it amplified ever since. He said that. But I don't know God and all that business. But what I know, what I can speculate is that maybe the walls are very important for creating turbulence with the property known as singularities and all that. If you don't have walls, presumably it behaves very much like that, but it is just on the border, so it might not remain like what it remains at the wall. So this is the speculation by all this. That means wall is really essential for turbulence. It may be just flat walls, maybe some roughness, maybe a cylinder somewhere, whatever. Or maybe the flow over a mountain somewhere, whatever, it's got to have a wall. Okay, I've really gone way out on the limb, but okay, it might inspire you to do something interesting.
So the problem is, so you're saying there is circulation, right? Circulation is constant, but once you hit a wall does generate vorticity, right?
Yes?
So then circulation is no more a constant, right? Because you get, it's injecting, it's a bit like your
This
boundary
is,
layer
this is my
paradox.
point. My point is that without that constant injection of vorticity, maybe you don't have turbulence. I mean, it just can't be turbulence anywhere without the.
What I'm asking is that the Kelvin-Helmholtz thing
Ah,
then breaks down because you now, if you follow it in Lagrangian fashion, maybe
yes.
it's fine. But since it's not going in Lagrangian space, right?
Yeah.
So there could be some leakages of what is the heat.
Yeah.
That could be the why the one-sided thing breaks.
So I'm not understanding every word you're saying, but I got the gist of it, I think. And the thing, of course, is near the wall, you have viscosity and things like that. There is no doubt about it. The problem about turbulence is always you have viscosity to start to deal with, and also the effect of the wall, which is different, not necessarily the same as viscosity, because it also gives you another boundary condition, which is that the normal velocity is 0. So wall has two different things, and it is very difficult to separate the two effects. And basically what I am saying is the wall has to be there somewhere nearby to inject these singular behaviors. And it could be because of the vorticity that's produced at the wall.
Okay, so I think we have done with questions. So with that, I would like to thank Professor Kriya Srinivasan.
Thank you, Annabelle.
So we have now, we had to discontinue the reminiscence session in the previous hall. So we would move on to that. Just before that, I just thought of adding that what Professor Balaji mentioned, that in 2020 February, he invited Professor Narasimha for a talk. And he spoke about cumulus clouds, and that room got completely full. People had to sit on the aisle. Today, thankfully, we had this room empty to use. So 6 years later, we, not surprisingly, have something similar repeat. So we have few other students, collaborators of Professor Narasimha and Professor Srinivasan who would share a few words now. So I'll first request Professor Owen Ramesh from Indian Institute of Science to share some of his memories.
Yeah. Thank you. Thanks very much indeed, Anubhav. I was a master's student in the mechanical engineering department of IISc. At that time, Oren had already moved to NAL. He was the director of NAL. And the first time I met Oren was not in IISc. There is this annual popular talk session in National College, Bangalore, in Basavangudi. In one of those, he gave this talk on turbulence. That's when I first saw him, and I was completely entranced by the kind of canvas he was painting. So after that, I joined as a PhD student in the aerospace department. And after a long time, I think he was still the director of NAL, and he used to, Narasimha offered probably for the last time a course on turbulence in the aero department. That is probably the last class. I still remember that's when I got introduced to this magic wand called matched asymptotic expansion, right? With which the power of that, right? And I think it was spectacular because what was striking about use of this tool, matched asymptotic expansion, were various fluid dynamic problems, used it for both turbulent flows as well as transitional flows, is that it was not, he was very insistent on marrying it to the physics of that. And I think one of the very well-known applications of non-turbulent but transitional flow application is the work he did with Rama. where this particular result about mixing layers, right? For example, these mixing layers are known to have zero Reynolds number, critical Reynolds number. But I think the work with Rama and one of his joint paper, right, where because of the non-parallel effect, it was shown to be something like 40 or something. Yeah, I think it is a beautiful application of matched asymptotic expansion. And of course, Rama's work itself about non-parallel, etc., where this machinery was used to great effect. So, as far as I was not a formal student of Narasimha. I was a student of Prabhu and Day. But effectively, he took great interest in my work, and we had very close collaboration. And this was further bolstered. Well, there was this meeting on transition which he arranged in Orange County in Coorg. Again, I think Rama was there, I think, in that meeting, right? I think he had asked me to sort of help him with organizing this meeting. And I remember traveling with him by car, and then that's when probably I got to know him very well. He became, ever since, I think, he was always been very, very, it was probably that particular trip which my association with Narasimha became very close and personal. So after I finished my PhD, the question about where do I go for postdoc, I was very keen on going to Israel, I think, and my supervisor, Prabhu, also was very keen I should go to Israel. But there was also this potential thing in Cambridge, and I remember distinctly this, they had called me for an interview to Cambridge. I finished that interview and returned back from Cambridge. Narasimha happened to visit Cambridge. I think his daughter was doing his PhD at that time in Cambridge. Maitreyi was doing in Cambridge. And I still remember that email he sent me. He said that, look, I went to this Cambridge, that lab. I have written a reference for you, right? This is the most expensive reference I've ever written. I hope you take up that position, because he knew that I was not very keen on Cambridge at that time. So yeah, I went on. Later, I came back and joined IISc Aerospace as a faculty member. Ever since, I think for the past, almost for the last 15 to 20 years, probably I had close association because I was practically the examiner for most of his students during that stage. And there was this particular meeting in a turbulence conference in Peking in 2009. I think Narasimha was visiting, that was the last time he visited China, and then I distinctly remember he was particularly chatty during that whole trip, all the way to the airport, all the way trip to China. He would not even sleep. He would talk about all kinds of things, his view on education, university systems. Because at that time, he was advocating start of undergraduate program in IISc. He was, I think it was the Caltech model, as he was calling that, where he was of the view that humanities also should be brought into the framework. So he was very, very, very particularly sort of chatty about this. He was he was not just confined to science, he was talk about all kinds of things. I think that 1 week in China, where we spent together, practically I was with him, he would share his views on everything. And I think much later, of course, we also talked about things. I think the last conversation ever I had with him was on music, for instance, because I had to give a popular talk on, I think, Sir C.V. Raman's work on musical instruments, especially the Indian string instruments like veena. And I spoke to Narasimha about that, because look, at that time he told me he was also a veena player when he was in his younger days. But he elaborated further on his thoughts about that, because he had always had this view about see, one of the main points I remember from that discussion is that the idea that history of science and mathematics is one theme which was very dear to him. And I think if you look at the history of mathematics, a logarithm, for instance, was thought to have started with Navier, I think John Napier, I think, 1600 or so. But then I think there was some observation that the frets in a Vena string are arranged logarithmically. So whether there is a recognition that the idea of logarithm predates all those work of Napier, etc., he was intrigued by them. When I pointed this to him, he was intrigued, but then he also told me about the other work on music, etc., the science of, the mathematics of music, etc. So I think especially towards the other interest towards the end of his last 20 years or so, he also developed, of course, interest in Vedanta and Yoga Vasishta, etc., about which I think he used to talk about it when he was in a very conversational kind of a mood. I will probably end with one story, right, to show the kind of impact he has had. It also brings in Srini into the picture. I was in a conference in the US. It was his 70th birthday conference, I think. After the conference, there was a trip some of us made to one of those rainforests, I think it's somewhere in the US. I think the people, I was traveling with some people, it included Ronald Panton and Gadalak, I think. Both Panton and Gadalak on the way to during the trip were gushing forth about Srini and his contributions, etc. Very soon, they were talking about if Srini has been so impactful in terms of his work, etc., they were talking amongst themselves, to themselves. How they were talking about the impact someone like Narasimha, his teacher must have had on him, etc. I suppose that this particular story, I suppose, to my mind, tells you about the impact of someone like Narasimha. So I think it says as much about Srini's impact as it did about Narasimha or Narasimha's impact on Srini. So with that, I would like to thank Anubhav for this opportunity. Thank you very much indeed.
Thank you, Professor Ramesh. May I request Professor Amrish Pandey from IIT Roorkee to come and share a few words now?
It's an honor for me to join this event. The inaugural chair occupant, Professor Srinivasan. So I was privileged to have worked with him for the last few years. And the only opportunity I had with Professor Narasimha was a few years ago in Bangalore. I had a meeting with him during a conference. And I consider myself fortunate that, I have met him in person, but I never got an opportunity to work with him. But having worked with Professor Srinivasan, I can imagine what kind of personality, and after hearing from all of you today and reading about him, what kind of scientist he was, and a gentle giant, as one of the ICTS newsletters, I learned a great deal about him. I'd like to talk about Professor Srinivasan because I have interacted with him quite a lot in the last few years. And I can now make connections that what the way of working and treating younger colleagues like us, and the insightful discussions when we have an opportunity to work together. It's really a pleasure of knowing these personalities, even though virtually or not knowing or not meeting in person, but just knowing Professor Narasimha this way is, I'm grateful that, yes, I'm part of this event. Just about Professor Srinivasan, so I remember this event, I was at IIT Kanpur starting my PhD, and He was visiting nearly 15 years ago, and he gave a talk on quantum turbulence. And I can recall that the auditorium was full, and everyone was very, very happy after the talk. So last week, I was discussing with one of the aerospace engineering professor from IIT Kanpur that how happy he was after hearing the talk from Professor Srinivasan. That, he spent 20 minutes on one single slide, and that kind of he could engage everyone, starting from the students to faculty members from all departments. So I just want to mention that whenever I feel low in energy, that okay, I'm not getting a lot of energy from myself to work on academics, so I just request Professor Srinivasan that, can we please meet once and discuss this, and after meeting with him, I always feel that yes, I can do something in academics and contribute. So I'm very happy that he is the inaugural occupant of this chair, and I really wish that this will be very fruitful for IIT Madras and for entire in university and institutes in India. Thank you so much. Thank you so much for having me, and congratulations.
Thank you, Professor Amrish. May I now request Professor Duburi Subramanian to share a few words?
Yes, absolutely. All right. Good afternoon. Well, I'm very, very happy to be here. I should first thank IIT Madras Applied Mechanics Department and Anubhav for thinking of me. Thank you for inviting me to be a part of this celebration. As someone said, this is really a celebration. So this celebration has two institutions which are very close to my heart and which I very deeply cherish. So one is IIT Madras. I've benefited a great deal from this institute as a student. So some 20 years ago, I walked in as a teenager, very excited about flight and wanting to understand how things fly. And then 4 years after that, I walked out as a certified aerospace engineer. And I've tried to maintain my connections to this institute strong. So it's always good to be back here. And the second institution is Professor Narasimha himself. So he's an institution by himself. He's an institution of science and technology and philosophy. He had very many facets to his life, and he was remarkably inspirational personality. So whenever I think of Professor Narasimha, there are a lot of thoughts. So to help me organize some of these things coherently, I'm going to in between read excerpts from a short article that I had written a little while after his passing, and then share some personal reminiscences. So as you all know, Professor Narasimha was a world-renowned researcher in the area of fluid dynamics and atmospheric sciences. He was also an aerospace technologist with great accomplishments. He was a scholar of Sanskrit and Kannada, an epistemologist of science and mathematics in ancient India, and an inspiring teacher and mentor. So in his 6-decade-long career, he played several visionary leadership roles in institution building, national technology programs, and in science and technology policy. So as I think Shrikant was saying earlier, like any one of these verticals, mortals like us would be very happy to have even a fraction of his achievement in any one of those verticals. So it was sort of, in many ways, a very singular personality. So all of you, or many of you here, know a lot about his science, but as a human being, he was remarkable, just a very remarkable person. And I was very, very fortunate. I consider it really a blessing to get to know him over the last 12 years of his life. So I was an undergraduate student here at IIT Madras, and I got this opportunity to work with him as part of a undergraduate summer research fellowship program that JNCSR, I hope they're still running that program because it's a fantastic program. By the way, there's a little connection here to this chair professorship because Arun Swaminathan, who has endowed this chair, also worked with Professor Narasimha as part of this fellowship. So he was my senior here. We didn't have an overlap, but I did hear of Arun through Professor Narasimha. He had done some very interesting work on wavelets. And it's funny that, when Professor Narasimha told me about Arun, I remember he was mildly disappointed that Arun went into finance after graduating from IIT Madras. But in a funny way, I suppose that is the career that has enabled this chair for the institute. When I got this, this was just before the days of, there was email, but these offer letters were back then were being still sent by speed post. I suppose now all of that is gone. People get all these offers by email. So I got a letter in my hostel, I remember, in a JNCSR envelope, and I opened it, and it said, "Congratulations, you got this fellowship." I was in my second year here, and he said that your mentor or advisor, whatever, will be Professor Roddam Narasimha. I was shocked. At least those of us who were students in the aerospace, we all knew, Narasimha was an absolute legend, right? And I was shocked that, he would take on undergraduate students over the summer. I didn't believe it. So I actually remember calling up the JNCSR fellowship office over phone. I think there was this person, Princey Pereira. I asked her, is there a did you guys mess up? Did you do a Control-C, Control-V error? No, he said, yeah, no, he's taken on two students and you're one of them. It took me a few minutes to believe that. So I was supposed to go and spend that summer at a university in the US, and then I canceled all those plans. I politely wrote to the professor who had made me an offer saying, look, I'm getting a chance to work with Professor Narasimha, so I'm sorry. He's like, yeah, you should just go and work with him. Don't waste your time coming here, right? So that was the start of a fantastic, 12 years association with him. So I'll just read some more excerpts from this article. So RN's curiosity-driven approach to research, long before it became a fashionable term in academic circles, coupled with his intellectual depth and breadth, enabled him to be deeply engaged across a spectrum of wide interests. And often his work had great relevance in the context of India, be it in terms of contemporary technological needs or the unraveling of civilizational scientific contributions. As a teacher and mentor, RN always remained accessible to his students, even during the phase of his career when he shouldered demanding administrative responsibilities and other tasks like that. I think some of my senior colleagues here will attest to that, Rama and ONR and others. Endowed with high levels of patience, he would liberally spend time to carefully explain concepts and ideas, sometimes even the most elementary ones, to students, which have had the great benefit of being a part of sessions like that. And this is the most fascinating thing. See, he was often deeply immersed in large technological programs throughout his entire career, but his love for little science from his student days remained very much intact. So I have this incident that is etched in my memory very deeply. So when I was at JNCSR that summer, and I was setting up this experiment for him, and he had placed a lot of trust in me, and he said, look, this is an empty corner of the lab, and you can start building this. This was a fairly large experiment involving a turbulent plume, which I was setting up. So I was very excited. I was designing this experiment. In one of those discussions, we were talking about which particular, I think it was a thermocouple that we should place in some part of the setup, which would be best, and so on. It was some little detail which we were having an involved discussion, and then his office phone rang. So he picked up the phone, and the person on the other side was speaking. I could hear him for about 2 minutes. He said, "Oh, is that so? Then let's cancel the launch and we'll discuss this at the next Space Commission meeting." And then he coolly puts down the phone and comes back and asks, okay, what about this thermocouple, right? I mean, that was mind-blowing. Here was someone who was giving very important advice that was relevant to national technology. And here I was a 19-year-old undergrad, and he had the bandwidth to I could never do that. I think most of us could never do things like this. So there are many such stories when it comes to Professor Narasimha. Like I said, I find it very hard to organize my thoughts whenever I think of him, because I've developed such a strong sort of emotional connection with him. So in closing, I just want to read out one other little paragraph, which I put a lot of thought when I was writing this. So in life, it is not often that one comes across true greatness, but when it happens, it is impossible to miss. Right? So I was very lucky that I encountered true greatness with Professor Narasimha. Arend's intellectual abilities and achievements, combined with his humility, simplicity, work ethic, and integrity, made him a singular personality. His life greatly exemplified the finest scientific, intellectual, and cultural traditions of the land that we live in. Right? So, again, I'm very happy to be a part of this celebration, and then, I should definitely say a few words about the first inaugural chair of the inaugural Roddam Narasimha visiting chair, Professor K.R. Srinivas. So I've had the pleasure and privilege of knowing Srini for about 15, 16 years now. I remember first meeting him at the 2009 APS DFD meeting in Minneapolis. I was a bit nervous to go and talk to him. I gathered the courage to go and introduce myself, and he's been very kind in all our interactions, and every time I talk to him, there's something profound that I take away. And I recently learned that he also wrote a very nice letter for my tenure at IISc, so I'm also very thankful for that. That lets me keep my job. So again, one of the earlier speakers was saying, I think in many ways, Professor Srinivasan is a very natural custodian to the great legacy of Professor Narasimha. So, it's impossible to think of a better inaugural holder of this chair. And there's just another interesting observation that just occurred to me as I was walking up to the stage. So right now, Professor Srinivasan holds the Satish Dhawan visiting chair at IISc. And Satish Dhawan, we all know, was Professor Narasimha's guru. So it's interesting now here he holds the Narasimha chair. So and we are both, I think both institutions are really privileged to have Srini and get his time. So congratulations, Professor Srinivasan, and thank you to IIT Madras and Arun for doing this. Yeah, thanks.
Thanks, Subbu. May I request Professor R.I. Sujit to come and say a few words?
Thank you, Anupam, for calling me for this occasion. It's a great honor to be here. I did not know Professor Narasimha. I have not interacted with him very closely because I was not a student and I didn't have too much opportunity to talk to him. But I had some, and they really counted. So first time I saw him was here in ICSR Hall. It was an Asian Congress in fluid mechanics. And I really wanted to meet him, but he was always in his Epsilon neighborhood. There were too many people trying to have conversations with him full time, and I could never find him in a state where I could go and speak to him. So eventually, I gave up. But that conference, I made friends with Rama. I was sitting next to her in a bus when we were coming back from lunch, and we had nice conversation. And subsequently, she invited me to JNCSR to give a talk. And there she introduced me to Roddam Narasimha. And this was really wonderful. And he came to my talk and asked a lot of questions, but really interesting. I mean, the most striking thing that I found was the kindness. He was really kind, and there is this little assistant professor who has not done anything, and he is like a national hero. But he was taking effort to find out how I was doing, what are my questions, and so on. So I understood, I got the point that he was a kind man, and I could ask him my questions. I had a lot of questions troubling me about, not really about turbulence or something. Our areas of work were quite different, at least at that time. I was not into turbulence. So subsequently reached out to him and asked him if I could ask some questions. And he was very kind in sorting out these things. These are very personal, I don't want to share them. But I met him many times, but I could not see his way of working or anything. But I had the opportunity to see him work as an engineer at the ISRO reviews, where there were some problems with some engines, and he was, and some missions and so on, and he was playing a very active role along with B. and Suresh. He was chairing the sessions, and it was really very nice to see his insightful comments and the way he works, and really like a hardcore hands-on engineer. He was paying attention to so much details and so on. My biggest memory is in Asian Congress, which was held in Bangladesh, where we were in a bus, and the only seat in the bus, I was the last one to enter, was the one next to Roddam Narasimha, and I sat there, and the bus got stuck in a traffic jam, and he was in a very happy talking mood. He gave me lots of advice, and some of my really troubling questions he answered. And we were stuck forever, and I was so happy, and I was really disappointed when the traffic jam cleared. At the time, he also spoke about this undergraduate program in IAC, and I was trying to convince him not to go for it, but he said, you know, I have this student called Duvuri Subramaniam from IIT Madras. Have you taught him? And we want a program full of students like him. This is what he said. And the last time I met him was in 2018 at a conference Rama organized, and there was a dinner to celebrate the 70th birthday of Professor K.R. Srinivasan. And I was really, really fortunate to sit in the same table, share the same table as both of them. And he was on a chatty mood, and he, even during the dinner and afterwards, he spoke a lot of things. Subsequently, I have not had any chance to meet him. I was good friends with Aditi. She was my neighbor, but I did not know that she was his daughter, because she was a very quiet person and would not, usually a very matter-of-fact kind of person. I have not had a lot of chance to interact with him, but each minute I spent with him was really valuable, and I think he really helped me to keep going and really try. And I think I had the courage to try the things I wanted to try, and he was the one who gave me that courage. And he said that, I'm sure I didn't have the courage to ask this question to anyone, and because I would have offended most people if I had asked this question. But during my first meeting itself, I understood that he's a national hero, but he's a cool dude. I mean, you can ask him anything, and he has this bandwidth to speak to any kind of person, including me. So I really benefited a lot from him, and I'm very grateful. I actually remember when he passed away, I heard some rumor that he has passed away, and I called up Rama to find out if it is true, and Rama was crying. I think anyone who interacted with him was deeply touched by his kindness, and I like I said, I had not had a chance to see his scholarship directly, only indirectly through his papers. And actually once I got a call from Gopalakrishnan whether he was inviting me to give the Roddam Narasimha talk at NAL. It was 2024. Actually, I started crying, and Gopalakrishnan couldn't figure out what was going on, why am I silent, but it was really emotional. So I think it's the same feeling. I know many of Roddam Narasimha's students, and it seems like they are a brand or a tribe or whatever, the class by themselves. They all have that value and the same appreciation of science, and even more importantly, the same kindness. So I will stop with that. Thank you all.
Thank you, Professor Sujit. I would like to request Mr. Srikanth to please come and share a few words.
Good evening. At the outset, my hearty congratulations and best wishes to Professor Srinivasan as he assumes this coveted chair, Professor named after Professor Narasimha. To borrow a term from one of Professor Narasimha's students, Professor Deshpande, he would always talk of the Dhawan Narasimha Gharana. So I'm sure Professor Srinivasan is the best qualified professor to take this Dhawan Narasimha Gharana forward. I'm sure he will do his best. I would also like to express my profound gratitude to this gentle giant about whom a lot of things have been said, very kind, very compassionate, very generous with his time, not just to scientists, but to a sore thumb in the middle of this audience of scientists like me. And when I saw the list, I was number 10 after Duiri, and I told him, batsman number 10 shouldn't bat for too long. So I will keep my speech pretty short. But of course, I can't forget Professor Narasimha for spending so much of time whether he was director NAL, whether he was in Department of Aerospace, director NIAS, or at JNC, to explain to me about anything, probably anything under the sun in science and technology, and of course about ISRO, because he was the member of the Space Commission. And I must express my sincere gratitude to Mr. Arun Swaminathan. I don't know if he's watching, but he's done a very noble deed by instituting this chair professorship. Dr. Srinivasan also was at the receiving end of my angst, if I might say, for 5 years, that I kept sending him mails asking him, why is it that nothing has happened in memory of Professor Srinivasan, in memory of Professor Narasimha. And 2 weeks ago, he just told me, come to Chennai, I'm giving a talk. He didn't say a word about the chair, but when I got the invitation, and then I realized he was being another humble soul like his guru. See, so there are a lot of anecdotes, lots and lots that a journalist would like to recall, but like I said, I'm batting at number 10 and being the sore thumb in the middle of all these scientists. I'd rather keep keep those anecdotes for another day. But then there was this one particular incident where I thought I upset him and his family. Of course, his family knew that he would prefer to take my calls even when he was not well and when he was in bed and when the doctors had advised him bed rest. But you see, there was this some inquiry that he and a former cabinet secretary, Professor Chaturvedi, held at ISRO, and when the then chairman went ahead and put aside the report of Professor Narasimha and Professor Chaturvedi and Professor Narasimha chose to resign as member of as member of the Space Commission. I broke the news, and little did I know it would have such an effect that the TV crews camped themselves outside his house the next morning, and then they trailed him. First, he had to go to, as coincidence would have it, he had an appointment with the same chairman. So later on, he told me, he said that particular person was trying to, couch his anger as much as possible, because you had your article on the front page that I had quit as a member of the Space Commission. And then they had these TV crews who were following him and Professor Narasimha to a hospital where Mrs. Narasimha had to undergo a medical checkup, and then they followed him back home. So at the end of it, at about 8 o'clock, Professor Narasimha stepped out of his house, brief statement read out to these TV crews, and then he wouldn't take any questions and went back. So I did apologize to Dr. Nilima after that, and generally because I would call at odd times. I would ask for him when I couldn't find him at home. I mean, at JNCSR or at the Department of Aerospace Engineering. So she said it was between Professor Narasimha and you. So if you if you wanted to take your calls, I'm nobody to to object. As director of NAL, he started a whole lot of civil aviation projects, and he kept me briefing first on the light canal research aircraft, on the 2-seater Hansa trainer, and then a 4-seater, and then came the SARAS. And then, of course, there's a saying that one should not be nasty about somebody, say no evil about the dead, but there were two very overzealous Air Force pilots who tried to do something ridiculous when they were on the short finals of while flying the SARAS. And then, they perished, and the aircraft perished, the flight engineers perished. And then it opened a Pandora's box, because a whole lot of inquiries followed, and then there were clashes between NAL and the DGCA as to how a prototype could be flown here, there, et cetera, et cetera. And this particular crash had turned the clock back by easily a decade on the SARAS. So, otherwise, it would have been definitely flying with the potential customers, because the Indian Air Force had already placed an order, and Professor Narasimha was very keen that what we know today as the UDAN project, that he wanted aircraft and little airfields to connect not just the metros but little city towns, considering that they were growing economically. So Flow Solver was another very interesting project that he encouraged Professor Sinha, his colleague in NAL, and they did wonderful work with the forecasting of the monsoon until IMD stepped in and issued a gag order that only IMDs is entitled to make announcements on the monsoons. So, I could go on and on, but I'm not Srishant, I'm Srikant. So, as Srishant at number 10 would have been more flamboyant and would have tried to, continue to bat, but I will wind up with a fervent appeal and rather beseech students and colleagues of Professor Narasimha to put together his biography, which has been in cold storage, unfortunately, for a long time. And it's also unfortunate that even Professor Dhawan's biography, a factual document of a legend like Professor Dhawan, hasn't as yet been out, and, because these are biographies that would certainly inspire students of the future generations, considering that how Professor Roddam and Professor Narasimha built the whole civil aviation, military aviation, or even the space program put together. Well, one unexpected spin-off of this rather long association with Professor Narasimha was the reunion of two long-lost colleagues, two long-lost cousins. So thanks to Professor Narasimha, I was reunited with Professor Srinivasan after probably a couple of decades. So my prayer once again to all students, former colleagues, and well-wishers of Professor Narasimha to put his biography together at some point, because the kind of passion with which he pursued science and technology, his humility, he was humility personified, and the way he explained things to extremely, a rookie scientist or a rookie journalist are something that need to be emulated. Thank you very much. Thank you, IIT Madras, for giving me this opportunity to say a few words about Professor Narasimha. Thank you.
Thank you. So just a minute, 1 minute. So we have a video montage from a few students of RN. We will just play them. But before that, Professor G.S. Bhatt, who many of you know, was also supposed to be here. So he couldn't make it, so he has sent a note which I will read it out for this audience. This is again for this occasion. Professor Roddam Narasimha, fondly called RN by his colleagues and students, was a multifaceted person. His contribution to various fields have been very original. He had been an outstanding teacher, a world-class researcher, a dynamic leader, and builder of institutions. Major part of his academic career was in ISC. He joined the Department of Aerospace Engineering ISC in 1962 and was associated with it till 1999. He founded the Center for Atmospheric Sciences, now called Center for Atmospheric and Oceanic Sciences, in 1982 and headed it till 1989. He was the director of the National Aerospace Laboratories during 1984 to 1993 and the director of the National Institute of Advanced Studies during 1997 to 2004. He started the Engineering Mechanics Unit at the Jawaharlal Nehru Center for Advanced Scientific Research, Bengaluru, and continued to work and guide students there till he breathed his last in December 2020. I'm privileged to be his student. Despite his busy schedules, Director NAL, Member of Scientific Advisory Committee to the Prime Minister of India, LCA program, Chairman of various committees, etc., when I was his PhD student, he never ignored his students. When he was NAL Director, he guided 6 PhD students who completed almost simultaneously. When in station, he used to come to ISC on Saturdays to meet students. If more urgent response was required, we used to send notes, manuscript drafts to his house through his secretary, and the response would come very next morning with clarification and or corrections, which used to be meticulously written with clarity. We were also welcome to meet him at his house and discuss. He and his wife, Mrs. Dr. Nilima Narasimha, would welcome us with a graceful smile. A brief meeting was enough to keep a student charged for the next 2 to 4 weeks. Many honors and recognitions that came his way, including Padma Vibhushan and the Fellow of the Royal Society, made no difference to his personal qualities, and he remained very humble and treated people of all walks of life with dignity. He was an extraordinary human being, winning a place in the hearts of many friends all over the world. Here I give 3 examples of the respect he commanded outside the academic community. There is a line in Sanjay Baru's book titled The Accidental Prime Minister, The Making and Unmaking of Manmohan Singh, wherein the author says that Roddam would have been a far superior national security advisor, referring to the then occupant of the position. Once Professor Narasimha told me that a Prime Minister called him personally and told,
I want you to head this inquiry committee to find out the truth. Once I happened to meet RN in the Frankfurt airport. He was nearing 80 then and was on his way to Washington, D.C. to take part in a high-level committee set up by NSF to draft policy decisions on future funding by NSF. The committee had only 3 members, including RN. I'm very pleased to know that IIT Madras has set up Roddam Narasimha Visiting Chair, and Professor K.R. Srinivasan, Srini, is its first occupant. A leading fluid dynamicist in the world, Srini is the most distinguished PhD student of Professor Narasimha. RN had great affection and respect for Srini, and it was mutual. Srini had initiated many actions to preserve RN's legacy. By his accepting this chair, Professor Srinivasan has given the prestige the chair deserves. I thank the sponsor, Mr. Arun Swaminathan, and IIT Madras administration for instituting the Roddam Narasimha Visiting Chair at IITM. Thank you, G.S. Bhatt. So we will now have the last bit of this program. I know it's a bit late, but even in the short duration in which we have conceived this, we have had an overwhelming response, and it's befitting of RN's stature that we hear some of the memories from his students who couldn't attend this in person. So we'll play the video montage of former students of Professor Roddam Narasimha.
Good afternoon in Chennai. I am Dr. Pinaki Bhattacharya. I am Associate Professor of Solid Biomechanics from the University of Sheffield in the UK. I am really grateful to Anubhav for giving me this opportunity to share my recollection of working with RN, in whose memory this chair has been established. At this time, I'm asleep, so I had to record this video and send over. And sorry about that. So going back and thinking about my time with RN, it was my MSc project that was supervised by him, in fact, jointly by RN and Professor Rama Govindrajan, who I'm guessing is also in the audience today. It was quite a formative period of my career. And even though at that time already I was aware how lucky I was to have them as supervisors, as time has passed, I have become more aware, for want of a better expression, of the size of the jackpot I had won then. My experience working with RN, of course, made a researcher of me, but more importantly, it changed me as a person. Now, the last of the 2 papers I co-wrote with RN and Rama was published, I think, 18 years ago. And over this period, my research has increasingly drifted away from fluid mechanics to the point that my job title for some time now has had the qualifier solid explicitly embedded in it. Yet, my time with RN continues to impact and inform me today, how I think, how I write, how I read, how I interact with others, and everything in between. Every year, for instance, when I explain the difference between, let's say, a long dash and a hyphen to a third-year undergraduate student, I remember that attention to detail and also the kindness and patience that RN showed me that afternoon so many years ago. Every time a PhD student shows me a new result, I feel I have to be answerable to RN before I can accept that result as correct and move on. Each time I need to learn a new method about a new area, I remember that RN was someone who had no trouble at all going from vibrations of strings to clouds to aircraft wings. And last but not the least, every day I get easily distracted by mundane meetings, noisy classrooms, tricky emails to answer, and so on. So when I sit down at the end of the day to write that research grant outline, I urge myself to attempt what RN would do so easily. Switch mid-sentence from explaining a PDE to me to pick up a phone call from a bureaucrat, deal with it, and then join the sentence where he left it with me. So in summary, Aaron's impact on me shows that what a mentor like him can do, and that impact lasts lifelong and transcends all kinds of disciplinary and geographic boundaries. So what my wish is for all the holders of the Professor Roddam Narasimha chair is that they continue to have such a transcendental impact on generations of researchers to come. With Professor Srinivasan as the inaugural chair, of course, it's a job done already. And I wish him the best, and I wish with all my heart IIT Madras the best to keep this going. Thank you so much, and have a nice day. Bye.
Hello everyone present there. I'm very happy to hear about the establishment of the Roddam Narasimha Chair Professorship at IIT Madras. This is truly a meaningful tribute to a life that shaped not only institutions and disciplines, but also generations of people, including me. I truly wish I could be present in person for the launch of this chair, but unfortunately my responsibilities here did not permit me to do so. I feel deeply fortunate to have been the last PhD student of Professor Roddam Narasimha, whom most of us lovingly called RN. Some of my most cherished memories and my most meaningful learning experience come from that period of my life. The technical understanding and the scientific rigor that I gained under his guidance shaped me who I am professionally. But RN's influence went far beyond academics. He taught me how to think, how to learn, and how to conduct myself with humility, integrity, and responsibility. In many ways, he helped me become not only a better researcher, but also a better person, a better citizen. I have many anecdotes and fond memories from my time with RN. I will share just one that has stayed with me over the years. During my PhD, RN submitted a proposal to GTRE DRDO based on my research work. Although the project was technically approved, it was delayed at the financial stage. One day, I received a call from a senior official at GTRE who remarked that the consultancy charges quoted by RN were far lower than what is typically approved for such projects. He suggested that I request RN to accept a higher amount so that the project could be cleared financially. When I spoke to RN regarding this, he simply said that he felt the amount he has asked for was adequate for the work that he promised. Eventually, the issue was resolved. RN often spoke about the importance of being frugal, especially in a country like India. He would fondly recall how in his early days of ISC, he fabricated pitot tubes himself rather than purchasing ready-made ones. From such moments, I learned what it truly means to be a responsible citizen. Finally, I warmly congratulate Professor Srinivasan on being the first occupant of this chair. This honor is very well deserved as he is undoubtedly one of the RN's finest students. I extend my heartfelt best wishes to everyone present on this occasion, the generous donor, Professor Kamakoti, Director IIT Madras, RN's family members, his students, and well-wishers. Thank you very much.
Good afternoon. My name is Sai Kishan Suryanarayanan. I'm an assistant professor at the University of Akron in Ohio. I'd like to thank the organizers for giving me this opportunity to share a few words via this recorded message. I got my PhD working with Professor Roddam Narasimha in 2015, JNCSR. I worked with Aaron from 2009 to 2015, and my doctoral dissertation was understanding certain aspects of turbulent flows, such as large-scale coherent structures and momentum and vorticity dispersal, from a point of view of statistical mechanics of vortices. So Aaron came up with this rather unique way of looking at turbulent shear flows in terms of vortices as molecules of turbulence. Through the many years I spent with Aaron, a couple of things that struck me the most. First was how approachable he was for the eminent individual he was. He was very approachable to all the students. We all had lunch together as a group with him every day, for the 6 years I worked with him. And I personally greatly benefited from the many informal discussions I had with Aaron over lunch. The second is the childlike curiosity is always exhibited, regardless of the level of expertise he has achieved in the field. He was always curious and was eager to kind of know what students thought of different topics. And I learned from Aaron that curiosity is the primary ingredient for doing quality research, and I hope to kind of carry that lesson forward and also spread it to the subsequent generations. So I'm very happy to know that IIT Madras has established this Roddam Narasimha chair, and that Professor K.R. Srinivasan is going to be the inaugural chair. I would like to convey my best wishes to IIT Madras and Professor K.R. Srinivasan for in this endeavor to carry Professor Narasimha's legacy forward with this chair position. Thank you.
Hello everyone. It gives me great pleasure to record this short video on the occasion of establishment of Roddam Narasimha Chair Professorship at IIT Madras, and I regret that I cannot be there in person to attend the launch event. I had about 10 years or more of association with Professor Narasimha, or RN as we all fondly called him. That started, when I joined him as a postdoc in 2009, where we worked on this cumulus cloud problem, both laboratory simulations and numerical simulation. And then I continued working with him even after that, after I returned to India as a faculty at IISc. And some of the things that struck me were his childlike curiosity. Even towards the end of his life, he was ready to get into a new problem, that was the pathogen transmission by human respiratory flows. His ability to hold a problem in his mind for a long time, go deep into it. The rationality he brought not only to the deep problems of turbulence, but also for the practical matters such as leakage of pipes. It was so wonderful working with him, to be around him. He created this atmosphere and energy around him that was welcoming. And I think towards that phase of his life, he probably was not as busy as he was earlier. So he had more time with his students and postdocs. And it was so refreshing to be around him, to be with him. And it is hard to believe that it has been 5 years now that RN is no more with us. But what a legacy he has created. He has left behind his shoes, but these are rather big shoes for any one of us to fill. And one can still see the vacuum, the void at the highest level, where he provided leadership in areas of aerospace, atmospheric sciences, history of science and mathematics, or even the fundamental physics of turbulence. But his footsteps certainly give us guidance, they inspire us, and also they show us what one person can achieve, the heights that one person can reach to, and also the breadth of activities one can touch as part of one's professional career. And I congratulate IIT Madras for the establishment of this chair. And I feel they would have found no better person than Professor K.R. Srinivasan to be its first occupant. As he is certainly one of the most accomplished students of Professor Narasimha. So I wish you all the success for this launch event. And I do hope to be able to come and visit you sometime. So all the best. Thank you.
I'm Konduri Aditya from the Indian Institute of Science. It is an honor for me to say a few words at this wonderful event. Professor Arun has been a great guru, mentor, and a grandfatherly figure to me. He did not just put a strong foundation for my career, but also evolved my personality. I am very happy that IIT Madras has started a chaired professorship on his name. I would like to thank IIT Madras and the donor in this regard. Congratulations to Professor Srinivasan for being appointed as the inaugural holder of the RM chair, recognizing his outstanding contributions in fluid mechanics and turbulence research. Thank you.
Good afternoon. I'm Ravichandran. I'm on the faculty of the Center for Climate Studies at IIT Bombay. I wish I were there in person for this event, but I thank Anubhav for giving me this opportunity to say a few words in remembrance of Professor Narasimha. I joined JNC in 2010 as a research fellow and then a PhD student with Rama Govindrajan and Arun. I think I'm right in saying I'm the last PhD student to graduate before Narasimha died. So I knew Narasimha for the last 10 years or so of his life. After having thought about this for the last couple of days, I want to mention a few qualities of Narasimha as a PhD advisor and human being that I wish to emulate in my own career and life. The most important of which is that Narasimha was curious, genuinely curious about subjects not having to do with fluid dynamics. In addition to his glittering career at IISc and NAL, Narasimha found time to make a study of the cottage industry that supplied the rockets that Tipu Sultan used effectively in his wars against the British. This would have been a fantastic historical study in its own right. But years later, Narasimha used this industry as an example in making profound observations about the philosophy of Indian science, the primacy of yukti over agama in Indian science. Narasimha was also, for his stature, given despite his stature and his vast experience and knowledge, Narasimha was genuinely humble and kind, and no student of his ever felt stupid asking a naive question in Narasimha's presence. I can attest to this from extensive personal experience. But now that I have students of my own, I know how much of a challenge this can be. This combination of deep curiosity and genuine humility and kindness meant that Narasimha was always surrounded by people with a wide range of opinions on any given topic, and he was able to have thoughtful discussions with any of them, even on contentious topics, without the conversations descending into bickering. This is a great quality to have, especially in today's age. When I joined IIT Bombay 3 years ago, I wanted to get IITB to establish a Narasimha chair professorship. But given the pressures of early career faculty positions, this has not yet happened. So I'm very pleased indeed that my old institute, IIT Madras, has established this Roddam Narasimha chair professorship, and I'm even more pleased that its first occupant is Professor Srinivasan Srini. I congratulate both IIT Madras and Professor Srini on this occasion.
So with that, I guess, I mean, there'll always be more people wanting to share their thoughts of RN and KRS, and but we will close this here. It has been a wonderful afternoon extending to the evening. And first, I would like to thank Professor K.R. Srinivasan for giving us this occasion to celebrate his work and also getting reminded of Professor Narasimha. So both opportunities was amazing for us. And also the guests who have come at such short notice, because this has elevated the occasion, the event itself, and also sharing your memories. So with this, I'd like to thank you, and we'll close this event.